Dispersion. Already we have been discussed under central tendency. Range. Simplest measure of dispersion, which is the difference between the highest and lowest values. Highest, lowest values, highest values. Difference between the highest and lowest difference in between these highest, lowest. What is the difference? This is the range. Interquartile range, less influenced by extreme values, less influenced extreme extreme values, but here less influenced, less influenced. This is interquartile range. Variance the most common way to measure dispersion for continuous data. For continuous data, the most common way to do measure dispersion for continuous data. Most common way measure dispersion continuous data. Continuous data provides an estimate of the average difference of each value from the mean. Provides estimate of the average difference. Provide the average difference. Okay. Provides estimate of the average difference of each value from the mean. This is the mean. So average for population. For population, sigma square equal to 1 divided by n summation of I equal to 1 equal to n x I minus mu of square. This is the population. We have to average total n from 1, then summation. Which one you have to summation? From 1 to n. From 1 to n. Okay, this is the n. You see, this is the 1 to n. Xi and mu. Xi here, x1 like this going on. No? We got to be minus mu for each one stage up to n. That is, we have to minus mu from this x, x1, x2, x3 up to xn. Then to be whole square, how much getting? You have to be squaring. Okay. For a sample, for a sample s square equal to s means sample here to be squaring. Here we are take 1 by n. From the n we are taking 1 only out. But here we have to be minus how much we are getting n. We have to minus from deduct from 1, and then after getting that we have to take 1. Okay, average. This is the one type of average. Then we have to save, but here mu, but here x bar. So up to n, here 1. Okay, so here all are to be summation up to n. Okay, n, this is here value x, each value x, x1, x2, x3, like that. Okay, then x bar to be minus, that is how much that xi, x1 each value. So total x they will give. So we have to this x bar we have to be deduct, and from this x1, x2, x3 each value, and then squaring also need to be square after getting this minus, after we have to be square. Okay, standard deviation for population, standard deviation, this one variance for a population, for a, you can consider this is a population. So sigma, then sigma root of sigma square. So you squaring, then sigma only will come. So cancelling, the sigma only will come. For sample also same like that. Okay. For particular say take sample. So uh, root square we can able to cancel. Now we are going to discuss about normal distribution. Figure 3.1, left side. Normal distributions have the same space, but same shape, but differ to their mu and sigma. Mu and sigma. All normal distributions have the same shape, but same shape, like this, like this. Sorry, like this, like this. Uh, all normal distributions have the same shape, but differs to the mu and the sigma. 0, when mu equal to 0, here 0 sigma is the 0.45. Here in x-axis, what will take? What will take? Minus 5 to plus 5. Okay, and then here 0 to 1. Okay, here while in 0 sigma, while in 0 sigma, 0.45. So here not particularly mentioning. This this is for this. Okay. and this one for this, this for this. Okay. Here also, when sigma is 0, sorry, mu is 0, this for this figure, sigma is the 0.5. When here mu is 0, then sigma is the 2.24. When mu equal to 2, when mu equal to 2, sigma is the 0.71. Okay, different. They are shifted by mu and stretched by sigma. Right hand side figure, percent data failing into specific ranges of the normal distribution. Here sigma, here sigma, here 0 to zero point 0.4. Okay, here in percent of that they are shifted by mu and stretched by sigma. Okay, uh, here say mu, okay, shifted to this value. Okay, percent of data failing into specified ranges of the normal distribution. When mu equal to uh, 0, 0, that time sigma how much percentage, 34 point percentage, 31.4 percentage, while in between minus 2 sigma to minus 1 sigma, how much, 13.6 percentage, in between minus 3 sigma to minus 2 sigma, 2.1 percentage, from 0 to approximately minus 3 sigma, not 0 here. Here approximately we can say minus 4 like that. So minus 4, 4 or 5 to 3.1 percentage. Here also same like that. In here left side, this is mirror side only, this one. So here mu to 0 to 1 sigma, 34.1 percentage. 1 sigma to 2 sigma, 13.6 percentage. 2 sigma to approximately 3 sigma, 2.1 percentage. 3 sigma to approximately 4 or 5.1 percentage. Normal, all normal distributions are symmetric. All normal distributions are symmetric, unimodal, symmetric. This is no symmetric only. Here negative, here plus. Mirror value, mirror image, single most common value, and they have a continuous range from negative infinity to positive infinity. Yeah, here mentioned negative infinity to positive infinity. The total area under the curve adds up to 1 or 100 percentage. This is the 100 percentage. 1 only, 0 to 1, 0 to 1, 0 to 1. Okay. Empirical rule for population that follows normal distribution, almost all the values will fall within 3 standard deviations above and below within mean 99.7. 2 standard deviations are about that 95 percentage. 1 standard deviation 68 percentage. Here didn't mention. The central limit theorem. As the sample size approaches infinity, as the sample size